So we just saw an example of an inner product on the polynomial spaces involving the integral. You could also have that as inner product on, say, the continuous functions or the differentiable functions. And furthermore, you can do a lot of other things here. For example, we integrated over 0 to 1. What if I integrate over some other interval? That's still going to give you a perfectly valid inner product. You can even get crazy here where you integrate with your functions, but you throw an extra function on here, so something like the e to the negative x squared. I've actually had to deal with that myself in some of my own research, where they put these extra things over here, and these are called weights. Now, not really needed for our class here, but the idea of having this weight there is you put more emphasis on some values of x and less emphasis on others. For example, e to the negative x squared, if you were to look at the graph of it, it looks something like this. That's pretty bad. But the idea is this high point is at 0, so the values of x near 0 would get more weight when you're doing the inner product compared to the values of x, say, at 1,000,000 or something. It's really small. You could also look back at, say, R2, and our normal inner product is if you have a point x1, y1 with a point x2, y2. The normal one is just to do the normal dot product, x1 times x2 plus y1 times y2. But if you wanted to, you can get a little creative here, and you can define a different inner product where you do x1 times x2 plus 5 times y1 times y2. So in that case, you want to make the y coordinate more important when you're talking about the inner product here. It's going to affect the answer more. You could put other numbers there in any kind of fashion you want. The one thing you can't do is you can't use negatives. And so you can go ahead and check. For example, let's say I do just switch it instead of plus 5 to minus 1 here. In that case, if you take a vector with itself, remember the answer is only supposed to give you 0 if the vector itself is 0, and that would break conditions 4 here. So breaks condition 4, which is going to make it not an inner product. So as long as you stay away from negatives, you can pretty much put whatever numbers you want there, and it'll work out to be an inner product here. You can also have inner products on matrix spaces. So for example, let's say we have 2 by 2 matrices, and I want to inner product the matrix A1, B1, C1, D1 with the matrix A2, B2, C2, and D2. And you just kind of define some sort of function here. Now there are some that will work well and some that won't work so well. And if you really want to play around with it, you can. But pretty much for this section, I will be giving you a definition of an inner product, and I'm going to ask you to do calculations with it. So what are we going to do? Once we have an inner product, once we have a function that has these properties, we're going to do the following things here. So the first is, if I want to find the length of a vector, all you're going to do is you're going to take the square root of that vector inner product with itself. So before we had the length of a vector was, squared was x dot x, and that's basically what we're doing here. We're just square rooting both sides. And so what this is going to do is it allows you to find the length of a vector in whatever crazy vector space you have. You can find the length of a vector as a polynomial. What's the length of this polynomial, which otherwise wouldn't make any sense. You can find now the distance between two vectors x and y. This is going to be by the norm of x minus y. We're going to call this the distance from x to y. So once we get our inner product, we get our norm, our length. Once we get that, we get our distance between things. Then on top of that, we can find angle between two vectors. Using the standard formula, cosine theta is x dot y over the length of x times the length of y. And so again, this is a way to define angles between, say, polynomials, or angles between matrices, or angles between arbitrary continuous functions. It's a really interesting way here. And I also want to point out that we can have different inner products on the same vector. So for example, you can have R2, the standard R2 inner product was x1, x2 plus y1, y2. And same R2, but we change the inner product to x1, x2 plus 5y1, y2. And if you do that here, you're going to get two different angles. They're going to have different theta values for the two different inner products. And what that kind of corresponds to is if you have, your vectors here and you get a theta, but then if you, stretch your y component, if you imagine like, space is being stretched here in the y direction in a factor of 5, let's say, then you're going to get a different theta called theta prime. And so this takes that into account. And you can find angles and all sorts of other things. And how about this? We can talk about orthogonal or perpendicular. So the idea of perpendicular is whenever the dot product of each other gives you 0. So you can talk about polynomials being perpendicular to each other, which again previously wouldn't make any sense. You can also talk about a unit vector. That would be whenever the length of it gives you 1. And the last of the computations that you're going to have to do here is going to be orthogonal projection. And you may or may not remember this. So the idea was you have a vector A and you have a vector B. You should have done this in Calc 3. And you want to see, well, what part of the vector B is in the same direction as A, right? What is this vector right here? And that was called the projection vector of B in the direction of A. And you may or may not recall before what it is. It is A dot B over A dot A times A. That was the formula for the projection vector. And so now in terms of inner product, the projection vector is going to be as follows. The projection of x in the direction of y is inner product x, inner product y, over inner product y with y times vector y. And we're going to use this to, again, do an orthogonal projection, which we'll see that later. So this is all the things we can do with it. Now let's do some examples where we do the calculations here.